is finish explaining the algorithm for calculating signatures of invariant Hermitian forms. So I made some progress with my slides, but not enough. I will try to give a reasonable talk today and spend the next couple of days cleaning up the slides to go with the talk and perhaps to provide some more details. But anyway, I'll just remind you one of the things that I was talking about last time. So remember, we had a notion of Hermitian dual representation, and there's a dangerous point. The notion of equivalence that we're using for quasi-simple representations is that's infinitesimal equivalence means that the Harish-Chandra modules are isomorphic. So if you have an isomorphism of Harish-Chandra modules between V pi and its Hermitian dual, that may not be implemented by a continuous map from V pi to its Hermitian dual. So the statement about the module being equivalent to its Hermitian dual is the statement about Harish-Chandra modules. And even if that's true, which means that you get an invariant form on a Harish-Chandra module, it might not exist on the GK module. So there's a theorem of Harish-Chandra that says it's all okay, that taking k finite vectors makes a bijection from the unitary dual of G onto, irreducible Harish-Chandra modules that have a positive definite invariant form. So because of this theorem of Harish-Chandra, it's okay to study just Harish-Chandra modules. If we find those the plan is, the slide says, Knapp and Zuckerman, we've been talking about parameterization of irreducible Harish-Chandra modules, that's these Atlas parameters, and taking the Hermitian dual. I haven't talked about the C, but never mind. Taking the Hermitian dual is an involution on this set of parameters, and Knapp and Zuckerman computed what the involution is. Maybe I will write it again, since I screwed it up several times. I might as well try to screw it up once more. So a parameter is, in sort of classical terms, is a theta stable Cartan subgroup. What I keep writing is lambda bar, which is an algebraic character of the fixed points of theta, and nu, which is in the -1 eigenspace of theta tensored over Z with the complex numbers. And, I'm not these things more or less up to K conjugacy, and this algebraic character is shifted by rho. this is supposed to correspond to an irreducible GK module. Well, I'll write pi. Then there's this Hermitian dual. Well, sorry, I should have written it on the other side. Oh, thank you. There's this pi h, the Hermitian dual, and that corresponds, what you do to the parameter is you keep the same h, the same lambda bar, and you replace nu by minus nu complex conjugate. I think I have this straight. There's confusing notation here. This bar on lambda means that it's a coset representative, and the bar on nu means complex conjugate. Well, okay. So well, so say Knapp and Zuckerman computed, well, this, I'll might as well, since I'm filling up the board, there's another notion which I probably won't get to today of the C Hermitian dual, and what that is, it's the same H, the same lambda, and just nu bar. Okay, so now I can be loud. Thank you very much. Okay, but I'm not on yet. I've forgotten what we did. Now, but it's not on. Now it's on. Thank you. And yeah, that bit is good. Thank you. Okay. So we know what this Hermitian dual operation is on parameters, and so we know which GK modules admit invariant forms, and what we are going to do is compute the signatures of those invariant Hermitian forms. That's the, because the Harishchandra theorem says that the unitary representations are the Hermitian representations where the form is definite. So that's the goal.
And David,
yes.
I just wrote on the board the minus sign, the change that the minus sign on the new bar makes. Is that a difference between pi and pi HC, or between pi H and pi HC?
It's between pi H and pi HC. The bar comes from the Hermitian part, and well, if I have a chance to talk about these things, anyway, so what? In this atlas world, this nu is automatically rational, and so every representation is C Hermitian. Because you just take the complex conjugate of the parameter and it doesn't change.
So the bar on the nu comes from the transition from P to pi C, not to pi HC.
The bar comes, yeah, this H corresponds to the bar on the nu. And
but you also put a minus sign.
That's and the minus sign on the nu, and here the H, I don't know how to say it. This is giving the bar on the nu and a minus sign, and the C gets rid of the minus sign. I'm not sure what the best way to say it is.
Okay, so C Hermitian means invariant under HC. Yeah.
Yes.
Okay.
Okay, so how do we compute signatures? So that's what I sort of said on Friday, what I should have said. And so now the real lecture for today. So as I say, in the atlas world, we have a set of parameters for our rational representations, and if we have a Hermitian parameter, what's supposed to be attached to it? First thing is a standard representation. This is the analog of a Verma module, and it has a unique irreducible quotient. This is the irreducible. And as Jeff said, one of the fundamental confusions in our notation is that whenever Atlas writes a parameter, it means one of these two things, and it's up to you to be clever enough to decide which. The standard representation is like a Vernal module, something very large, but not too complicated. The irreducible quotient is something much smaller and interesting, but difficult to understand. So, well, digressions are always good. The character formula for a Verma module of highest weight, well, let me write lambda plus rho, highest weight lambda minus rho. It is something like e to the lambda over a Weyl denominator. And of course, the character formula for a finite dimensional representation of highest weight lambda minus rho, it is the sum over w and w minus 1 to the w e to the w lambda over. So these two things, which should be either familiar to you or accessible to you, that's the difference between standard modules and irreducible modules. This Verma module is gigantic, but it's built in a very simple way. This finite dimensional is the interesting thing. It's much smaller, but it's in many ways more complicated. Okay, but anyway, we have those two things, and the theory depends on working with this deformation family, with taking these parameters and deforming the continuous parameter. So I have this, well, I didn't write the Atlas version, but we've talked a lot about those Atlas versions. You just take this continuous parameter and scale it. Look at 0 less than or equal to t less than or equal to 1. And what happens is this Hermitian condition, well, I should write it explicitly. This representation has an invariant, the irreducible representation, J of this parameter, has an invariant Hermitian form if and only if this parameter h lambda bar nu is equivalent to h lambda bar, well, minus nu. This is the, I'll just write it for these rational values of nu. That's the condition, and that's the same thing as saying that this h lambda bar and t nu is equivalent to h lambda bar minus t nu for 0 less than or equal to t less than or equal to 1. Because equivalence means that there's some Weyl group element that does something. And so if you have one Hermitian representation, you automatically get a one parameter family, and that's what we're going to work with. And at the same time, well, these standard modules come with a family, an algebraic family of invariant Hermitian forms. So, what do I want to say? The first key property is that if you look at one of these invariant forms, the radical of that form is the kernel of this quotient map that's mentioned up here from the standard module to the irreducible quotient. And so the form on the standard module descends to a non-degenerate form on this irreducible quotient. At t equals 0, well, I'm lying a little bit, but never mind. This representation is tempered, and so the form is definite. So here's the plan for computing signatures. We'll start with the known signature at t equals 0, and then look at this deformation family. The form is varying in a continuous way, and so the signature is constant except when the form becomes degenerate, except when this, well, when this, yeah, so one of the key properties that I didn't write is, I mean, I said this earlier, that this quotient, well, the standard module, gamma t, is irreducible, except for a discrete set of values of t. So it's only at that discrete set that the signature can change, and what we're going to do is compute the changes at those reducibility points and put all that together and end up with a formula for the signature at t equals 1. So that's the plan. So what's this look like for SL2? So let me write down again the principal series representations that I wrote for SL2 well, eventually I put these on, I did either even or odd, but let's just look at even trigonometric polynomials on the circle. So the basis is these e to the im thetas for m an even integer. And I won't write again these Lie algebra elements, the basis that I used, but AH was a basis vector for the Lie algebra of SO2. It's a rotation, an infinitesimal rotation. So that acts on WM by multiplication by M. And then these two other operators were root vectors for this SO2 cartan, and they act like this. So, when I first wrote the principal series, I said that the definition I wrote differed from Atlas by a shift of 1. So I went back and changed the slides so that it no longer differs from Atlas. So I added 1 to new. So this is rewriting history, which is unfair, but now anyway, these formulas correspond to the Atlas parameters new. And
I think this is the same notation as in the ref card.
good, excellent, I hope so. And I had also screwed up as many signs as it was possible to screw up in writing the formulas. And
Even or an odd number of signs.
definitely an odd number, yes. And I think that the formulas written here may be exactly correct. You know, that also possibly not. Anyway, the formulas that I wrote before were these ones in the first column. So this is trigonometric polynomials on the circle. That space can be identified with its Hermitian dual, well, with its rotation finite Hermitian dual, using the L2 inner product on the circle. You just, these e to the im thetas are an orthogonal basis. So that's what's written here. And then the way if you write an operator on this space as a matrix in the basis of these e to the im thetas, then of course the Hermitian transpose, the way you compute it is you take the transpose matrix and you put a complex conjugate over the entries. Now, the definition of this Hermitian transpose, so how do I say it? So if I don't know, pi w is a GK module, then the definition pi h wh is defined by pi h of some z is you take pi of sigma 0 of Z, and then you take the Hermitian transpose of that. So that's how you're supposed to compute the Hermitian transpose of a representation. So we need to know, did I write? I didn't write here. The sigma 0 of H is minus H, and sigma 0 of X is, I think, and damn it, I forgot the minus sign. Now I think it's correct. I think sigma 0 of X is Y. So what that says is that in our setting, this Hermitian transpose operation on X is minus pi of Y Hermitian transpose. So this matrix has, this has non-zero entries at the I think maybe at m plus 2 and m, and this thing has non-zero entries at m and m plus 2, and what the entry is, that's it's this thing. This non-zero entry is m minus nu minus m plus
There's a shift in M as well.
yeah, that's why I'm
Just say it's at M minus 2M.
maybe it's something like well, the entry of this pi of Y matrix, I don't know, I tried to do this last night, but at any rate, when you take the negative, you get something like m minus nu plus 1, and that corresponds exactly, well, I'm saying this terribly. The conclusion is that this pi nu, the Hermitian dual, is pi minus nu. That's what's written. I mean, I computed this, minus nu complex conjugate in general. That's what's written up here. So I computed the various Hermitian transposes and got almost the same formulas as before, except that nu is replaced by minus nu bar. So that's the conclusion, and well, it's what I've said several times, the imaginary values of nu are Hermitian representations, and the invariant Hermitian form, in that case, it's just this positive definite inner product. And that's the unitary principal series. But there are more more Hermitian representations. So what do they look like? So now I want to look at real values of nu. So this what I'm saying is that pi nu is usually isomorphic. Those parameters are actually conjugate, so usually the representations are the same, and so we expect to get invariant forms. So I want to understand those invariant forms. And here I wrote what the real form does to our basis, so I got that right. And that's the condition for a form to be invariant. And we know that this basis Wm is a basis of eigenvectors for H, and if you plug that fact into this invariant notion and take Z equals H, what you find is that these Wm's must be an orthogonal basis. So Wm paired with Wn has to be some real scalar times a Kronecker delta. Okay. Now we have these formulas for x and y, and if you plug those formulas into the definition of invariant, you get this equation. I'm using these formulas, and I guess W is Wm, and W prime is Wm plus 2, something like that. And this is the equation that comes out. And those things tell you that for every non-negative nu, this representation has a unique invariant Hermitian form subject to the property that W0 has length 1. And what that form looks like